Welcome, and thank you for settling in with us tonight. Wherever you are right now, whether you are tucked gently into your bed, resting quietly on your couch, or simply closing your eyes for a soft and peaceful moment, you are exactly where you need to be. Find a comfortable position, allow your body to sink gently into wherever you are resting, and let your breathing slow to its own natural, unhurried rhythm. Tonight, we are going to take a long and peaceful journey through the Milky Way Galaxy, the ancient, vast, and endlessly beautiful river of stars we have called home for all of human history. Drifting quietly from one quiet wonder to the next, letting each soft and distant fact wash gently over you like a slow, warm tide. There is nothing you need to do, nowhere you need to be. Simply rest, breathe, and allow the quiet wonders of the universe to carry you softly towards sleep. Right now, at this very moment, as you rest and breathe and let your eyes grow heavy, you are living inside the Milky Way Galaxy, not looking at it from the outside, but nestled gently within one of its graceful, curving spiral arms, surrounded on all sides by hundreds of billions of stars. This is not something you need to travel to or search for. It is simply the cosmic home you have always lived in, quietly spinning through the universe at an almost unimaginable speed, yet feeling perfectly, beautifully still from where you lie. The light from the stars above you, the ones you can see on a clear, dark night, all belong to this same great family of light and gas and ancient dust. You are not separate from the galaxy. You are a part of it, as much as any star or nebula or quiet cloud of cosmic mist. The name Milky Way comes from the ancient Greek phrase *galaxias kyklos *, which means milky circle, and it was given this name simply because our ancestors, lying on their backs in open fields on clear, moonless nights, looked up and saw a soft, creamy band of light arching gently across the entire sky. That faint, glowing ribbon they observed was not a cloud or a mist. It was the combined glow of hundreds of billions of stars, so numerous and so distant that their individual light blended together into one continuous, silky stream of pale luminescence. Every ancient civilization that ever gazed upward had its own name for this band. The Romans called it *via lacti*, the road of milk, and many indigenous cultures across the world described it as a river, a path, or a trail of scattered seeds. The same quiet glow that moved ancient poets and philosophers to wonder is still there tonight, waiting patiently above you, unchanged and unhurried. The Milky Way Galaxy is estimated to be approximately 13.6 billion years old, which means it began to form only a few 100 million years after the Big Bang itself, when the very first currents of matter in the universe began to slowly gather and swirl and coalesce under the gentle, irresistible pull of gravity. To put that into a softer kind of perspective, if the entire age of the universe were compressed into a single calendar year, the Milky Way would have formed sometime in the very first days of January, and our own Earth would not appear until early September. The oldest stars within our galaxy, ancient, cooler, reddish-orange stars known as red dwarfs, have been burning quietly and steadily for nearly as long as the galaxy itself has existed, with lifespans so long that many of them will still be glowing long after our own sun has completed its life. There is something deeply soothing about this kind of age, the idea that the universe has been quietly at work, building and shaping and illuminating, for longer than the human mind can truly hold. Within the soft, sweeping arms of the Milky Way, there are estimated to be somewhere between 100 billion and 400 billion individual stars, each one a sun of its own, burning at its own temperature, emitting its own color of light, and potentially hosting its own family of planets orbiting quietly around it. If you were to count one star per second without stopping, it would take you more than 3,000 years just to count to 100 billion, and that count would still leave open the possibility of 300 billion more. Some of these stars are enormous and blazing blue-white, burning so intensely that they exhaust their fuel in just a few million years. Others are small and cool and red, burning so gently and efficiently that they may shine for hundreds of billions of years without interruption. Every single one of them, regardless of size or color or temperature, is a sphere of plasma held together by its own gravity, quietly generating the energy of nuclear fusion deep within its core, a slow, sustained, almost meditative process that has filled this galaxy with light since its very beginnings. If you could somehow step outside the galaxy and look down upon it from a great height, the Milky Way would appear to you as a breathtaking, slowly rotating pinwheel, a flat, luminous disk with a bright, softly glowing central bulge surrounded by long, gently curving spiral arms that sweep outward like the trails of light left by a slow-spinning sparkler on a warm summer evening. Astronomers classify our galaxy as a barred spiral galaxy, which means that the central bulge is not perfectly round but is instead elongated into a gentle rectangular bar shape, from the ends of which the spiral arms extend outward in graceful, sweeping curves. This bar structure at the heart of the Milky Way is thought to be roughly 27,000 light-years in length, and it acts somewhat like a slowly turning cosmic engine, gradually channeling streams of gas and dust toward the center of the galaxy where new stars can be born. The overall appearance, seen from above, would be something like a vast, slowly turning flower of light, layered, symmetrical, and radiantly beautiful against the deep darkness of intergalactic space. The Milky Way Galaxy, measured from one outer edge to the opposite outer edge, spans approximately 100,000 light-years in diameter, and a single light-year, to offer a gentle sense of scale, is the distance that light travels in an entire year, moving at roughly 186,000 miles per second without stopping. This means that even if you could somehow travel at the speed of light, the fastest speed permitted by the known laws of physics, it would still take you 100,000 years to cross from one side of the Milky Way to the other, journeying in a perfectly straight line through a river of stars. More recent research has suggested that the true outer edges of our galaxy, including its faint stellar halo and outermost star clusters, may extend the effective diameter to nearly 200,000 light-years, making the Milky Way even larger and more generously proportioned than once believed. And yet, despite this almost incomprehensible size, the Milky Way is itself considered a relatively average-sized galaxy in the broader context of the universe, quietly mid-sized among its cosmic neighbors. The spiral arms and their gentle names. The Milky Way has 4 primary spiral arms, each one a long, sweeping river of stars, gas, and dust that curves outward from the central bar in a graceful, pinwheel pattern. And each of these arms carries its own quietly evocative name that reflects its history of discovery and the astronomers who mapped it. The 2 largest and most prominent arms are called the Perseus arm and the Scutum Centaurus arm, both of which are dense with bright, newly forming stars whose blue and white light gives them a vivid luminosity against the darker regions between the arms. The arm in which our own solar system currently resides is a somewhat smaller, secondary arm called the Orion arm, sometimes also referred to as the Orion spur, a modest, gently curved offshoot that branches away from the Perseus and Sagittarius arms like a quiet side street branching from a grand, brightly lit boulevard. There is something rather comforting in knowing that our home, our sun, our planets, our moon, rests not at the center of the galaxy's grandest structures, but quietly along a smaller branch, a gentle, unhurried offshoot of the larger cosmic design. Our sun, and with it all 8 planets of our solar system, is located approximately 26,000 light-years from the center of the Milky Way, settled comfortably within the Orion Arm, positioned roughly halfway between the galaxy's dense, bright core and its outer, quieter edges. This particular location is considered by astronomers to be something of a Goldilocks zone of the galaxy, far enough from the energetic, crowded galactic center to avoid the intense radiation and gravitational disturbances that would make stable planetary systems difficult to maintain, yet close enough to the inner galaxy to be enriched with the heavier chemical elements produced by older generations of stars. From our position within this spiral arm, we orbit the galactic center at a speed of approximately 514,000 miles per hour, completing one full orbit of the galaxy, a journey that astronomers call a cosmic year or galactic year, approximately every 225 to 250 million years. The last time our solar system was in this exact same position along its galactic orbit, dinosaurs had only recently disappeared from the Earth, and the continents were still drifting toward their current configurations. At the very center of the Milky Way, hidden behind layer upon layer of interstellar dust and gas that absorbs most visible light, there lies a region known as the Galactic Center, an extraordinarily dense, luminous, and active region filled with ancient star clusters, massive molecular clouds, and a population of stars so tightly packed together that the night sky, if you could stand on a planet there, would blaze with the light of millions of nearby suns. Nestled at the absolute heart of this central region is one of the most remarkable structures in the known universe, a supermassive black hole called Sagittarius A*, pronounced Sagittarius A*, which contains a mass equivalent to approximately 4 million of our suns compressed into a region of space smaller than our own solar system. In April of 2022, the Event Horizon Telescope collaboration released the first ever direct image of Sagittarius A*, showing a glowing ring of hot, orange-gold light surrounding a perfectly dark central shadow, one of the most quietly profound photographs ever captured by human science. Despite its enormous mass, Sagittarius A* is currently in a relatively quiet, dormant phase, gently sipping in small amounts of surrounding material rather than actively consuming large quantities, a resting giant at the center of a galaxy still softly, steadily spinning. While the Milky Way is approximately 100,000 light-years wide from edge to edge, it is comparatively quite thin. The main stellar disk is estimated to be only about 1,000 light-years thick through most of its span, making it, proportionally speaking, much thinner relative to its width than even a single sheet of paper would be relative to its own dimensions. However, the galaxy is not perfectly flat. It has a gentle, sweeping warp along its outer edges, curving slightly upward on one side and slightly downward on the other, a shape that astronomers believe was caused long ago by the gravitational influence of the Milky Way's 2 largest satellite galaxies slowly pulling on the outer disk over billions of years. The central bulge, by contrast, is considerably thicker than the surrounding disk, rising and falling roughly 10,000 light-years above and below the galactic plane, a softly glowing, rounded region packed with older, yellower stars that formed in the galaxy's earliest epochs. Imagining the Milky Way from the side, it would look something like a very flat, gently warped disk with a soft, round bulge at its center, like a spinning top that has settled into its long, graceful rotation. The Milky Way does not spin like a rigid wheel, where the outer edge moves at the same speed as the inner regions. Instead, different parts of the galaxy rotate at different speeds, with the stars near the central bar moving at different rates than those in the outer spiral arms, a behavior that astronomers describe as differential rotation. Interestingly, our Sun's orbital speed around the galactic center, roughly 514,000 miles per hour, keeps it moving at almost exactly the same speed as the spiral arm pattern itself, which means our solar system tends to remain within or near the Orion arm rather than drifting in and out of denser, more active arm regions over time. This stable, steady orbital relationship between our Sun and the spiral arm is considered one of the factors that has allowed our corner of the galaxy to remain relatively calm and undisturbed for long stretches of time, a quiet consistency that may have been favorable for the development and long-term stability of life on Earth. There is something almost meditative about this image, our little solar system sailing smoothly and steadily through the galaxy, keeping pace with the slow, enduring rotation of the great spiral arm around it, like a leaf floating quietly in a slow, circular current of a very gentle river. If you were to add up all the visible stars, gas, dust, and nebulae within the Milky Way, everything that emits or reflects light and can therefore be directly detected, you would account for only a small fraction of the galaxy's total estimated mass, roughly 4 to 5% of what gravity calculations suggest must actually be there. The vast majority of the Milky Way's mass, approximately 90% or more, is thought to exist in the form of dark matter, an invisible, non-luminous substance that does not emit, absorb, or reflect any form of light and therefore cannot be seen or photographed directly, but whose gravitational influence on the visible matter of the galaxy is very clearly and precisely measurable. Dark matter forms what astronomers describe as a halo, a vast, roughly spherical cloud that surrounds and extends far beyond the visible disk of the Milky Way, stretching outward for hundreds of thousands of light-years in every direction and acting as an invisible gravitational scaffold that holds the galaxy together and maintains the shapes of its spiral arms. Without dark matter, the Milky Way as we know it could not exist in its current form. The visible stars and gas would not have enough combined gravity to prevent the outer parts of the galaxy from gradually dispersing and flying apart, like water droplets spinning off the edge of a slowly turning wheel. The Milky Way is not alone in its corner of the universe. It is accompanied by a family of smaller satellite galaxies that orbit around it the way moons orbit around planets, drawn into loyal, gravitational partnership with our galaxy over the course of billions of years. The two largest and most prominent of these satellite galaxies are the Large Magellanic Cloud and the Small Magellanic Cloud, a pair of irregular, somewhat cloud-like galaxies that are visible to the naked eye from the southern hemisphere as two soft, separate smudges of pale light sitting quietly beside the main band of the Milky Way in the night sky. The Large Magellanic Cloud is located approximately 160,000 light-years away and contains tens of billions of stars of its own, while the Small Magellanic Cloud, at roughly 200,000 light-years, is somewhat smaller and less densely populated, though both are actively forming new stars at an impressive rate. In total, the Milky Way is known to have more than 50 confirmed satellite galaxies, small, quiet companions of varying sizes, most of them dwarf galaxies with only a few million or billion stars each, all of them slowly orbiting the great spiral in long, graceful paths that take billions of years to complete. The Milky Way is a member of a gravitationally bound collection of galaxies known as the Local Group, a relatively modest gathering of more than 50 galaxies that share a common gravitational neighborhood spanning roughly 10 million light-years of space. The three largest members of the local group are the Andromeda Galaxy, the Milky Way, and the Triangulum Galaxy, with Andromeda being the largest of the three, a grand, majestic spiral containing approximately 1 trillion stars, visible to the naked eye on a clear, dark night as a soft, elongated smudge of light in the constellation Andromeda. The remaining members of the local group are predominantly small dwarf galaxies, scattered across the neighborhood in irregular distributions, each one held in gravitational relationship with either the Milky Way or Andromeda as the two dominant anchors of the group. Together, the local group sits within an even larger cosmic structure, the Virgo supercluster, which contains thousands of individual galaxies spread across a region roughly 110 million light-years in diameter, making our local neighborhood a small but meaningful part of a much larger cosmic tapestry. It might seem, from your quiet vantage point on Earth, that the universe is perfectly still around you, but the Milky Way itself is moving through space with a surprisingly purposeful velocity, drawn steadily by the gravitational pull of a massive concentration of matter known as the Great Attractor. The Milky Way, together with the entire local group of galaxies, is moving toward the Great Attractor at a speed of roughly 1.4 million miles per hour. A speed that sounds extraordinary but is, on cosmic scales, a relatively calm and unhurried drift through the vast fabric of space and time. The Great Attractor itself is located approximately 250 million light-years away in the direction of the Centaurus and Hydra constellations, a region of space so dense with galaxy clusters and dark matter that its gravitational influence extends across hundreds of millions of light-years in every direction. Even as all of this motion unfolds, the Earth rotating, orbiting the Sun orbiting the galaxy moving toward the Great Attractor. From where you lie right now, everything feels perfectly, serenely still, and that stillness is entirely real and entirely yours. Surrounding the flat disk of the Milky Way like a vast, diffuse crown is a structure known as the stellar halo, a roughly spherical cloud of old, sparsely distributed stars, star clusters, and streams of stars that extends outward for hundreds of thousands of light-years in every direction beyond the main galactic disk. The stars within the stellar halo are among the oldest in the entire galaxy, many of them remnants of the Milky Way's earliest formation period or the leftover stars of small satellite galaxies that were gradually absorbed and dismantled by the Milky Way's gravity long ago. These halo stars are generally low in what astronomers call metallicity, a measure of the abundance of elements heavier than hydrogen and helium, because they formed before the universe had time to produce large quantities of heavier elements through stellar nucleosynthesis, the process by which stars forge heavier atoms within their cores. The stellar halo also contains a population of globular clusters, ancient, densely packed spherical swarms of hundreds of thousands of stars, which orbit the galactic center in long, sweeping paths, like a scattered retinue of faithful attendants surrounding the galaxy from a great and respectful distance. The Milky Way is home to approximately 150 to 180 known globular clusters, compact, roughly spherical collections of ancient stars so tightly bound together by gravity that they have held their shape for nearly as long as the galaxy itself has existed, enduring for billions of years without dispersing into the surrounding space. Each globular cluster contains anywhere from tens of thousands to several million individual stars packed into a region of space only a few hundred light-years across, a density so extraordinary that if our solar system were located at the center of a typical globular cluster, the night sky would contain many thousands of stars brighter than Sirius, the brightest star currently visible from Earth. Many of the Milky Way's globular clusters are thought to be older than the disk of the galaxy itself, with ages estimated at 10 to 13 billion years, suggesting that they may have formed in the very earliest phases of the galaxy's assembly, possibly even before the great spiral structure had fully taken shape. These clusters drift in long, elliptical orbits through the stellar halo, passing through and above and below the galactic disk over the course of hundreds of millions of years, like slow, ancient sentinels quietly circling the home they have always known. The total mass of the Milky Way Galaxy, including all of its stars, gas, dust, stellar remnants, and dark matter, is estimated by astronomers to be approximately 1 trillion times the mass of our own Sun, though some estimates place the figure closer to 1.5 trillion solar masses when the full extent of the dark matter halo is accounted for. This immense total mass is expressed by astronomers using the shorthand of solar masses, since measuring in ordinary Earth-based units would require numbers so large they would lose all practical meaning. A trillion suns worth of matter, all held together in the graceful, slowly rotating structure of a single spiral galaxy. Interestingly, the Milky Way is not the most massive galaxy in the local group. That distinction belongs to the Andromeda Galaxy, which is estimated to contain between 1 and 2 trillion solar masses, though recent observations have suggested that when dark matter halos are fully accounted for, the two galaxies may be more evenly matched in mass than previously thought. Regardless of how these measurements are refined over time, the sheer, quiet enormity of the Milky Way's mass, held together invisibly, rotating steadily, burning softly with the light of hundreds of billions of stars, is a fact that invites a particular kind of comfortable, humble wonder. One complete orbit of our solar system around the center of the Milky Way is called a galactic year or a cosmic year, and this extraordinary journey takes approximately 225 to 250 million Earth years to complete, carrying our Sun and all its planets on a vast, sweeping circuit around the galactic center at a speed of roughly 514,000 miles per hour. Since the formation of our solar system approximately 4.6 billion years ago, the Earth has completed roughly 18 to 20 of these full galactic orbits, meaning our planet has traveled around the Milky Way about 20 times since it first coalesced from a spinning cloud of gas and dust around a newly formed star. During the most recent galactic year, the last 225 million years of Earth's history, the continents have drifted significantly from their previous positions. Dinosaurs have appeared and then gradually given way to mammals, and early primates have evolved, slowly and quietly, into the form of life now lying here reading these words. The concept of a galactic year offers a beautiful reframing of time, a reminder that even the deepest stretches of Earth's geological history are contained within just a handful of cosmic revolutions, and that the universe moves at a scale of time that makes every human moment feel both very small and very precious. Between the stars of the Milky Way, the space that might appear empty at first glance is actually filled with a diffuse mixture of gas and dust known as the interstellar medium, a vast, tenuous fabric of material that connects all the stars of the galaxy in a continuous, if extremely thin, cosmic atmosphere. The interstellar medium is composed primarily of hydrogen, roughly 7 to 5% by mass, along with helium and trace amounts of heavier elements, distributed across the galaxy in a variety of phases ranging from very cold, dense molecular clouds to warm, diffuse regions of neutral gas to hot, ionized plasma regions where energetic young stars have blown bubbles of radiation into the surrounding space. This material is not merely passive filler, It is the reservoir from which new stars and planetary systems are born, and the recipient of the material return to space when old stars exhale their outer layers or explode into supernova events, cycling heavy elements back into the galaxy's available pool of building materials. The interstellar medium gives the Milky Way much of its soft, painterly texture when viewed in false-color radio or infrared images. Long, glowing filaments of hydrogen, dark, silhouetted patches of cold dust, and bright, swirling regions of ionized gas illuminated in shades of red, green, and blue by the energetic light of nearby stars. Scattered throughout the spiral arms of the Milky Way are regions of extraordinary beauty known as nebulae, vast, slowly swirling clouds of gas and dust that glow in luminous colors ranging from deep crimson red to soft jade green to pale, silvery blue, depending on their composition, temperature, and the nature of the light sources illuminating or energizing them. The most spectacular of these are emission nebulae, in which the intense ultraviolet radiation from hot, newly formed stars causes the surrounding hydrogen gas to absorb energy and then release it as visible light, particularly the deep red glow of hydrogen alpha emission that gives so many nebulae their warm, rosy appearance in long-exposure photographs. Some of the most famous nebulae in the Milky Way include the Orion Nebula, visible to the naked eye as a soft, fuzzy star in the Sword of Orion, the Eagle Nebula, home to the iconic pillars of creation, towering columns of dense gas and dust within which new stars are slowly assembling themselves, and the Carina Nebula, one of the largest and most active stellar nurseries in the entire galaxy. The word nebula comes from the Latin word for mist or cloud, and it is a fitting name. These regions do indeed look like luminous mist when seen through a telescope, soft and swirling and endlessly graceful, as though the galaxy itself was slowly breathing. In addition to the ancient, compact globular clusters found in the stellar halo, the Milky Way contains thousands of younger, more loosely organized collections of stars called open clusters, groups of tens to thousands of stars that form together from the same molecular cloud and still share a common region of space, though they are gradually drifting apart over time. The most famous open clusters visible from Earth are the Pleiades, a group of several hundred stars most visually dominated by a tight gathering of bright blue-white suns surrounded by a soft, wispy blue reflection nebula, and the Hyades, the closest open cluster to our solar system at a distance of only about 150 light-years, whose stars form the characteristic V-shaped face of the constellation Taurus. Open clusters are relatively short-lived on cosmic timescales. The gravitational interactions between their member stars and the tidal forces of the galaxy gradually disperse them over hundreds of millions of years, until their individual stars are scattered independently throughout the galactic disk, having long since lost their original grouping. It is thought that our own Sun was born as part of such an open cluster, a group of sibling stars that formed from the same molecular cloud approximately 4.6 billion years ago, and have since dispersed so thoroughly throughout the galaxy that we have no way of identifying with certainty which other stars were once our Sun's nearest neighbors at birth. The Milky Way, like all galaxies, is composed overwhelmingly of hydrogen, the simplest and most ancient element in the universe, along with helium, the second element, together accounting for well over 90% of all ordinary, non-dark, matter in the galaxy by mass. The remaining fraction of the galaxy's composition consists of heavier elements: oxygen, carbon, nitrogen, iron, silicon, magnesium, sulfur, and dozens of others, all of which were forged inside the cores of stars over billions of years through the process of stellar nucleosynthesis and then dispersed back into the interstellar medium when those stars reached the ends of their lives. This process of stellar cycling, stars forming from clouds of hydrogen and helium, fusing heavier elements in their cores over millions or billions of years, and then returning those elements to space at the end of their lives, has progressively enriched the Milky Way's chemical composition over time, making each new generation of stars slightly more chemically complex and diverse than the generation that came before. Every atom of carbon in your body, every atom of oxygen you breathe, every atom of iron in your blood, all of it was assembled inside the core of a star that lived and died before our own sun was born, and all of it is now a part of you, here, in this quiet moment, on a small planet inside the Milky Way. New stars are being born within the Milky Way at a current estimated rate of approximately 1 to 3 new stars per year, a gentle, steady pace of cosmic creation that takes place within the densest, coldest regions of the molecular clouds scattered throughout the galaxy's spiral arms. New stars are being born within the Milky Way at a current estimated rate of approximately 1 to 3 new stars per year, a gentle, steady pace of cosmic creation that takes place within the densest, coldest regions of the molecular clouds scattered throughout the galaxy's spiral arms. The process of star birth is a remarkably slow and gradual one. A dense region of a molecular cloud must first collapse under its own gravity over the course of hundreds of thousands of years, slowly compressing the gas and dust into a rotating disk of material with a dense, hot protostar at its center, before the central object eventually becomes massive and hot enough to ignite nuclear fusion and begin shining as a true star. The disks of gas and dust that form around young protostars are also the birthplaces of planetary systems. The same swirling material that feeds the growing star can gradually coalesce into rings, then clumps, then planetesimals, and eventually into fully formed planets, moons, asteroids, and comets, all orbiting their new sun in an orderly arrangement. The Milky Way has been creating stars at varying rates since its earliest days, with periods of particularly intense star formation in its ancient past, meaning that the galaxy we live in today is the product of billions of years of this quiet, patient, creative process of condensation and ignition. One of the most remarkable features of the Milky Way that exists largely invisible to ordinary observation is a vast, sweeping stream of stars and debris known as the Sagittarius stream, a long, looping ribbon of stellar material that wraps around the entire galaxy. The remnant of a small satellite galaxy called the Sagittarius dwarf elliptical galaxy that has been slowly consumed and shredded by the Milky Way's gravity over the past several billion years. As the Sagittarius dwarf galaxy has repeatedly passed through and orbited around the Milky Way, gravitational tidal forces have gradually stripped away its stars, stretching them out into a long, curving filament that now traces a complete loop around the galaxy, a ghostly, dispersed river of stars spanning nearly the entire extent of the Milky Way and its halo. This stellar stream was only definitively identified and mapped in the late 1990s and early 2000s, when astronomers analyzing the positions and velocities of large numbers of stars in the Milky Way's halo began to recognize the coherent, stream-like pattern among stars that had previously seemed to be random members of the galactic halo population. The discovery of the Sagittarius stream is a reminder that galaxies are not static, fixed structures but dynamic, living systems, slowly growing, consuming, and incorporating the matter of smaller companions over vast stretches of cosmic time. When you look up at the Milky Way on a clear, dark night and trace that glowing band of light across the sky, you may notice a long, dark lane running down the middle of it. A dark channel that seems to split the glowing river of stars into two parallel streams of light, stretching from the constellation Cygnus in the north all the way down to Centaurus in the south. This dark lane is known as the Great Rift, and it is not an absence of stars but rather a foreground structure, a long, continuous band of cold, dark interstellar dust and molecular clouds lying between our solar system and the more distant stars of the inner galaxy, absorbing and blocking their light before it reaches our eyes. Indigenous cultures around the world took great notice of this dark lane and gave it profound meaning. In the astronomical traditions of some Andean peoples, for example, the dark patches along the Milky Way were understood as animals and figures in their own right, forming a dark constellation astronomy that was as sophisticated and carefully observed as the star-based constellations of European astronomy. The dust clouds that make up the Great Rift are also among the most active star-forming regions in the inner galaxy. These same dark, cold, light-blocking clouds are the dense molecular reservoirs within which gravity is quietly, patiently assembling the next generation of stars and solar systems. Among the many different types of objects within the Milky Way, one of the most precisely regular and quietly remarkable is the pulsar, a rapidly rotating neutron star that emits beams of electromagnetic radiation from its magnetic poles, sweeping those beams through space like a lighthouse sweeping its beam across a dark sea. Pulsars are the remnants of massive stars that have completed their life cycles and collapsed under gravity into an extraordinarily dense object called a neutron star, in which a mass comparable to that of our entire Sun has been compressed into a sphere only about 12 to 15 miles across, a density so extreme that a teaspoon of neutron star material would weigh approximately 1 billion tons on Earth. What makes pulsars particularly remarkable is the extraordinary regularity of their pulses. The most stable pulsars, known as millisecond pulsars, rotate hundreds of times per second and maintain their rotation rates with a precision comparable to the most accurate atomic clocks ever constructed by human technology. There are currently more than 3,000 known pulsars in the Milky Way, each one quietly spinning in the darkness between the stars, sending out its regular, rhythmic beam of radio waves like a soft, cosmic heartbeat. A reminder that even in the vast stillness of interstellar space, the universe maintains its own slow, patient pulse. When a star like our own Sun reaches the end of its hydrogen-burning life, several billion years from now, it will gradually expand into a red giant, gently puffing out its outer layers into the surrounding space in a slow, luminous exhalation that will create a beautiful planetary nebula, before its core collapses and settles into a small, incredibly dense remnant called a white dwarf. White dwarfs are roughly the size of the Earth but contain a mass comparable to that of the original star, making them extraordinarily dense objects, though far less extreme than neutron stars, and they no longer generate energy through nuclear fusion, but instead slowly radiate away the residual heat built up over their long lifetimes, glowing steadily in white, yellow, or eventually red hues as they cool over billions of years. The Milky Way contains an estimated 10 billion white dwarfs, the quiet, cooling embers of stars that once burned brightly and lived out their full lifetimes, most of them invisible to the naked eye but detectable with sensitive telescopes as faint points of white or blue-white light scattered throughout the galactic disk and halo. In the far future, when the universe is many times older than it is today, these white dwarfs will eventually cool completely into inert, dark spheres known as black dwarfs. Though the universe is currently not old enough for even a single black dwarf to have yet formed, meaning every white dwarf that exists is still quietly glowing, still releasing its ancient warmth into the surrounding darkness. Woven through the gas, dust, and stars of the Milky Way, completely invisible but measurable through its effects on charged particles and radio waves, is a large-scale magnetic field that permeates the entire galaxy, a cosmic magnetic structure that threads through the spiral arms, the interstellar medium, and even the galactic halo in complex, slowly evolving patterns. The galactic magnetic field is thought to play an important role in regulating star formation. The magnetic pressure within dense molecular clouds can resist gravitational collapse, potentially slowing the rate at which new stars form and influencing where and how often stellar birth occurs throughout the galaxy. The magnetic field also plays a role in guiding cosmic rays, high-energy charged particles that travel through the galaxy at speeds close to the speed of light, causing them to spiral along magnetic field lines rather than traveling in straight paths, which means that most cosmic rays reaching Earth cannot be traced directly back to their original sources. The galactic magnetic field was detected and mapped using observations of polarized radio waves emitted by electrons spiraling around magnetic field lines in the interstellar medium, a subtle, beautiful signature of an invisible but genuinely pervasive cosmic structure that quietly shapes the behavior of matter throughout the entire galaxy. The Milky Way looks remarkably different depending on which type of electromagnetic radiation you use to observe it, and each wavelength reveals a different, equally beautiful layer of the galaxy's complex, multi-layered structure, like peeling back successive veils to reveal different aspects of the same magnificent subject. In visible light, the galaxy appears as the familiar band of stars and dust we can see with our eyes, bright starlight punctuated by dark dust lanes and glowing nebulae. In infrared light, the dust becomes partially transparent, and the warm glow of cooler stars and dust clouds is revealed, making the galaxy look richer, fuller, and more golden. In radio wavelengths, the cold hydrogen gas of the interstellar medium becomes visible as sweeping, continuous structures spanning the full extent of the galactic disk, tracing the true large-scale architecture of the spiral arms with a clarity that visible light observations cannot achieve through the obscuring dust. In X-ray and gamma-ray wavelengths, the galaxy reveals a more energetic face, glowing regions of superheated plasma, rapidly spinning pulsars, and the subtle but pervasive glow of cosmic ray interactions, all of it layered together into the single, complex, endlessly facete object we call the Milky Way. In 2010, NASA's Fermi Gamma Ray Space Telescope revealed one of the most unexpected and spectacular features of the Milky Way ever discovered: two enormous, roughly symmetrical lobes of high-energy gamma-ray and X-ray emission extending approximately 25,000 light-years above and below the galactic plane, centered precisely on the galactic center where Sagittarius A* resides. These structures, now known as the Fermi bubbles, are thought to be the remnants of a major energetic event that occurred in the relatively recent past, possibly a period of intense activity from Sagittarius A* several million years ago when the black hole was actively consuming large amounts of surrounding material and generating powerful jets of energy that inflated the surrounding gas into these vast, glowing lobes. The Fermi bubbles extend outward from the galactic center perpendicular to the plane of the galactic disk, forming a shape somewhat like two enormous soap bubbles pressed against each other at the galactic equator, structures so large that they represent a significant portion of the Milky Way's total volume, yet invisible to ordinary light-based observation. Though the discovery of the Fermi bubbles was initially puzzling, no one had predicted structures of that scale radiating from the galactic center. They have since become one of the most studied features of the Milky Way, quietly reshaping our understanding of the energy history of the galactic center region. Our Sun is considered a third-generation or population 1 star, meaning that it formed from molecular cloud material that had already been chemically enriched by two previous generations of stars that lived and died before our Sun was born, contributing their heavier elements back to the interstellar medium. The earliest stars in the Milky Way, known as population 3 stars, are believed to have been composed almost entirely of hydrogen and helium, completely lacking the carbon, oxygen, iron, and other heavier elements that characterize the Sun and the Solar System, simply because no previous stars had yet existed to produce and distribute those elements. The second generation of stars, population 2, formed from gas that was slightly enriched with the products of those first stellar generations. They are the old, metal-poor stars still found in globular clusters and the galactic halo, their chemical composition frozen in time as a record of the galaxy's early chemical state. Our own Sun, with its relatively high abundance of heavier elements, could only have formed after many previous stellar generations had completed their cycles, which means that the very existence of Earth, life, and human beings required the patient, multi-billion-year work of countless previous stars, each one living and dying to gradually build up the chemical richness the universe needed. Surrounding the supermassive black hole Sagittarius A** at the center of the Milky Way, within the innermost few hundred light-years of the galaxy, there lies an extraordinary region known as the Central Molecular Zone, a vast reservoir of dense, warm molecular gas that contains approximately 50 million solar masses of material, representing one of the richest concentrations of molecular gas anywhere in the galaxy. Despite this enormous reservoir of raw star-forming material, the Central Molecular Zone produces new stars at a rate far lower than would be expected given its density. A puzzle that has intrigued astronomers for decades and that is thought to be related to the turbulent, highly energetic environment near the galactic center, which may prevent the gas from cooling and collapsing into stars as readily as it does in the quieter outer regions of the galaxy. The Central Molecular Zone also contains several massive star clusters, including the Arches Cluster, the Quintuplet Cluster, and the central cluster immediately surrounding Sagittarius A**, which are among the densest concentrations of massive, young stars anywhere in the Milky Way, burning brilliantly in the intense environment near the galactic core. The entire Central Molecular Zone is also suffused with magnetic fields much stronger than those in the outer disk, high-energy cosmic rays, and the gravitational influence of Sagittarius A**, creating an environment so complex and dynamic that astronomers have compared it to a miniature, extraordinarily active galaxy within the galaxy. The Milky Way is pervaded by a continuous, invisible rain of cosmic rays, high-energy particles, primarily protons and atomic nuclei stripped of their electrons, that travel through the galaxy at speeds approaching the speed of light, carrying energies far beyond anything that can be produced in any particle accelerator on Earth. The origin of cosmic rays has been a subject of scientific investigation for over a century, and while their exact sources are still not completely understood, the leading candidates are supernova remnants, the expanding shells of energetic material left behind when massive stars explode, which can accelerate charged particles to extraordinary speeds through a process of repeated interactions with the shock waves generated in the explosion. Some of the most energetic cosmic rays detected on Earth carry energies so high that their exact source cannot be the Milky Way itself. They are thought to come from sources in distant galaxies, but the majority of lower-energy cosmic rays that continuously bathe our planet are believed to be products of energetic processes within our own galaxy. Cosmic rays that reach Earth's atmosphere generate showers of secondary particles as they collide with air molecules, and these cascades of secondary radiation are constantly bathing the Earth's surface in a faint, continuous background of high-energy particles, a quiet, invisible reminder that even in what appears to be empty space, the galaxy is always present and always active. Beyond the well-known Magellanic Clouds, the Milky Way hosts an extended family of smaller satellite dwarf galaxies, diffuse, faint, gravitationally bound companions that orbit at varying distances, most of them so dim that they were only discovered in the past few decades through careful surveys of the sky. Among the most notable are the Sagittarius dwarf spheroidal galaxy, currently being slowly consumed by the Milky Way's gravity, contributing its stars to the Sagittarius stream mentioned earlier, and the Canis Major dwarf galaxy, which sits very close to the galactic disk and may be in an even more advanced state of tidal disruption. More recently, surveys like the Sloan Digital Sky Survey and the Dark Energy Survey have revealed numerous previously unknown dwarf satellite galaxies hiding in the halo, some of them so faint and sparse that they contain only a few thousand stars spread over an area larger than the full moon in the sky, making them almost impossibly difficult to identify against the background of the much richer main galaxy. These dwarf companions are of great scientific interest because their internal dynamics, particularly the way their stars orbit within them, provide some of the clearest observational evidence for the existence and distribution of dark matter, since these small galaxies appear to be almost entirely dominated by dark matter rather than by their visible stellar content. One of the most elegant tools in astronomy for understanding the stars of the Milky Way is the Hertzsprung-Russell diagram, a graph that plots the luminosity of a star against its surface temperature and reveals that stars do not scatter randomly but instead fall into distinct, meaningful groupings that reflect their age, composition, and evolutionary stage. The majority of stars in the Milky Way, including our own Sun, fall along a diagonal band called the main sequence, which runs from hot, luminous, blue-white stars at the upper left to cool, dim, red stars at the lower right, and represents the long, stable phase of a star's life during which it is steadily fusing hydrogen into helium in its core. Above the main sequence lies the region of giant and supergiant stars, older, evolved stars that have expanded dramatically after exhausting their core hydrogen, while the lower left corner of the diagram is occupied by white dwarfs, the hot but dim remnant cores of stars whose outer layers have already been shed. Each individual star in the Milky Way, every one of the hundreds of billions of suns spread across the galactic disk, can in principle be placed somewhere on this diagram, and the overall distribution of stars across the diagram tells the story of the galaxy's stellar population, its age, and its history of star formation. The disk of the Milky Way is not perfectly flat. A careful mapping of the positions of thousands of Cepheid variable stars in the outer regions of the galaxy, published in 2019, confirmed that the galactic disk exhibits a noticeable warp, curving gently upward on one side of the galaxy and downward on the other in an S-shaped, asymmetric distortion that becomes more pronounced toward the outer edges. This warping of the galactic disk is thought to be the result of the gravitational influence of the Milky Way's satellite galaxies, particularly the large and small Magellanic Clouds, whose combined gravitational pull has gradually tugged the outer regions of the disk away from a perfectly flat configuration over billions of years. The warp is not a static feature but is thought to be slowly rotating, a phenomenon called precession, meaning that the direction in which the disk curves above and below the galactic plane is slowly drifting around the galaxy over time, like the wobble of a slowly spinning top that has been pushed slightly off its central axis. The discovery of this dynamic, rotating warp added another layer of gentle complexity to our picture of the Milky Way, confirming that even the large-scale shape of our galaxy is not fixed and eternal but is instead a slowly, continuously evolving product of gravitational interactions that have been unfolding over billions of years. Approximately 4 to 5 billion years from now, the Milky Way and the Andromeda Galaxy will complete a slow gravitational approach that has been underway for most of the history of the universe, eventually merging together in a long, graceful collision that will unfold over hundreds of millions of years. The term collision is somewhat misleading, because the stars within galaxies are so widely spaced that the two galaxies will largely pass through each other, with individual stars extremely unlikely to actually collide. Instead, the interaction will be primarily gravitational, with tidal forces dramatically reshaping both galaxies, pulling long streams of stars out into space and gradually transforming the two spirals into a single, large elliptical galaxy. The merger is expected to occur in stages, a first close pass that will stretch and distort both galaxies' structures, followed by a gradual retreat, then a second approach, and eventually a final merger over a time span of billions of years. And throughout this entire long process, the night sky as seen from any planets that still exist will gradually transform into something quite different from what we see today. Scientists have nicknamed the future merged galaxy Milkomeda, a gentle combination of both galaxies' names, and simulations suggest that the Sun, if it still exists at that point, will likely be repositioned to a different location within the new, combined, elliptical structure, surrounded by a far richer and more densely populated sky than the one we look up at today. Light, the fastest thing in the known universe, traveling at approximately 186,282 miles per second, would still take an extraordinarily long time to cross the full extent of the Milky Way Galaxy from one edge to the other, even at its breathtaking constant speed. A photon of light departing from one side of the Milky Way's roughly 100,000 light-year diameter would require 100,000 years to arrive at the other side, meaning that if you could watch a beam of light begin its crossing of the galaxy at the moment of the birth of the oldest known cave art in human history, that beam would still have barely begun its journey. This also means that when you look at the glowing band of the Milky Way in the night sky, the light from the most distant stars within that band left its source many thousands of years before the light from the nearest stars, meaning the entire sky you observe is a mosaic of different moments in time, layered together into a single visual impression. The light from the center of the Milky Way, from the stars surrounding Sagittarius A*, left its source approximately 26,000 years ago, at a time when the Earth's most recent glacial period was still underway and the first anatomically modern humans were beginning to spread across the planet's continents. Before most people think of the Milky Way as a source of radio waves, they picture the visible night sky, but the Milky Way is in fact one of the brightest sources of radio emission in the entire sky, emitting radiation across a wide range of radio frequencies from a variety of different physical processes operating throughout the galaxy. The most important of these radio sources is the 21-centimeter hydrogen line, a specific frequency of radio emission produced by neutral hydrogen atoms throughout the interstellar medium, which was first predicted theoretically in 1944 and first detected in 1951. And which has since been used to map the distribution of hydrogen gas across the entire Milky Way with a precision and completeness that visible light observations, blocked by dust, can never achieve. In addition to hydrogen emission, the Milky Way emits radio waves through a process called synchrotron radiation, in which electrons moving at near-light speed spiral around magnetic field lines and emit radiation as they do so. This diffuse synchrotron emission contributes a continuous, low-level background of radio waves that suffuses the entire galaxy. Radio astronomy has been one of the most transformative tools for understanding the large-scale structure of the Milky Way, allowing astronomers to see through the obscuring dust of the galactic plane and map the positions of star-forming regions, spiral arm structures, and the properties of the galactic center in a way that would have been completely impossible using only visible light. One of the most elegant patterns in the Milky Way's stellar population is a systematic variation in chemical composition with position in the galaxy. Stars closer to the galactic center are generally more metal-rich, containing higher proportions of elements heavier than helium, than stars in the outer regions, reflecting the fact that star formation has been more intense and more prolonged near the center, resulting in faster and more thorough chemical enrichment of the available gas. This gradient in stellar chemistry, known as the galactic metallicity gradient, provides astronomers with a kind of chemical map of the galaxy's star formation history, indicating where and when the most active phases of stellar birth and death occurred over the galaxy's long lifetime. The Sun's chemical composition places it at or slightly above the average metallicity for stars of its age in its region of the galaxy. It is neither unusually metal-rich nor unusually metal-poor, but sits comfortably within the typical range for a middle-aged star in the middle region of the galactic disk. This chemical averageness of the Sun is one of the reasons that planetary scientists do not consider our solar system's composition to be particularly exotic or unusual. The abundance of heavy elements available to build rocky planets and the molecular building blocks of life was well within the normal range for stars forming in the Milky Way at the time our Sun was born. Since the first confirmed detection of an exoplanet orbiting a Sun-like star in 1995, astronomers have discovered thousands of planets beyond our solar system within the Milky Way, and current statistical analyses suggest that planets are not the exception but the rule, with the average star in the Milky Way hosting at least one planet and many hosting multiple planets in stable orbital configurations. Based on these findings and the estimated number of stars in the Milky Way, astronomers have concluded that our galaxy likely harbors hundreds of billions of planets, a staggering abundance of worlds, spread across the spiral arms and disk of the galaxy, each one unique in its size, composition, temperature, and orbital characteristics. Among the most intriguing subset of these worlds are those located in the habitable zones of their host stars, the range of orbital distances at which liquid water could theoretically exist on a planet's surface, and current estimates suggest that billions of such potentially habitable worlds may exist within the Milky Way alone. The Kepler Space Telescope, which operated from 2009 to 2018, detected over 2,600 confirmed exoplanets within a relatively small portion of the galaxy, providing the statistical foundation for these extraordinary extrapolations about the total planetary population of the Milky Way. The central bar of the Milky Way, the elongated, rectangular structure that cuts across the galactic center from which the two major spiral arms emerge, is not merely a passive structural feature but is an active, dynamic component that plays a significant role in shaping the distribution and motion of gas and stars throughout the inner galaxy. The bar rotates with the galaxy but at a different pattern speed than the surrounding disk, and as it rotates, it exerts gravitational torques on the gas and stars in the inner regions of the galaxy, driving gas inward toward the galactic center, influencing the shapes and locations of the spiral arms, and creating resonance patterns in the orbits of stars throughout the inner disk. The length of the Milky Way's central bar is estimated at approximately 27,000 light-years from end to end, and its long axis is thought to be oriented at an angle of roughly 25 to 45 degrees relative to the line connecting the Sun to the galactic center, a geometry that has been refined through observations of stellar kinematics and infrared brightness distributions across the inner galaxy. The presence and behavior of the galactic bar is one of the features that places the Milky Way firmly in the barred spiral category of galaxy morphology, a category shared by roughly 2/3 of all observed spiral galaxies in the universe, suggesting that bars are a common and long-lasting feature of spiral galaxy evolution rather than a transient or unusual phenomenon. One of the most valuable classes of stars for understanding the scale and structure of the Milky Way are variable stars. Stars whose brightness changes over time in regular, predictable ways, and particularly a subset known as Cepheid variables, which pulsate in a periodic cycle whose duration is directly related to their intrinsic luminosity. This relationship between pulsation period and intrinsic brightness was discovered by astronomer Henrietta Swan Leavitt in 1912, working at the Harvard College Observatory, and it transformed our ability to measure distances in the universe. By observing how long a Cepheid's pulsation cycle takes and comparing its observed brightness to its known intrinsic brightness, astronomers could calculate exactly how far away it was. Cepheid variable stars served as the primary tool by which Edwin Hubble, in the 1920s, was able to demonstrate that the Andromeda Nebula was in fact a separate galaxy far outside the boundaries of the Milky Way, a discovery that fundamentally changed our understanding of the universe's scale and the Milky Way's place within it. Today, Cepheids and similar variable stars continue to be used as precise standard candles for measuring distances throughout the Milky Way and beyond, quiet, pulsating lights scattered across the galaxy, blinking with a reliability that has allowed astronomers to construct an ever more precise three-dimensional map of our galactic home. The Hyades star cluster, the closest open star cluster to our solar system at a distance of only about 150 light-years, is a gentle, scattered group of several hundred stars that forms the distinctive V-shaped face of the constellation Taurus in the winter sky, immediately surrounding, though not including, the bright reddish-orange star Aldebaran, which is actually a foreground star and not a member of the cluster. The Hyades cluster is estimated to be approximately 625 million years old, a young cluster by stellar standards, and its member stars are generally similar in temperature and color to our own Sun, making it a useful and nearby reference point for studying the properties of middle-aged stars in the galactic disk. Because the Hyades is so close and so well-studied, it serves as a cornerstone of the cosmic distance ladder, the series of overlapping measurement techniques that astronomers use to establish distances at progressively greater scales, with each technique being calibrated against the more precise measurements possible at closer distances. On a clear winter evening, looking at the soft V-shape of Hyades in the constellation Taurus, you are looking at one of the most carefully measured and thoroughly understood groups of stars in the entire galaxy. A modest, graceful little family of suns lying just down the cosmic road from our own. The Milky Way contains an estimated 2 to 4% of its ordinary matter in the form of solid dust, tiny particles of silicate minerals, carbon compounds, water ice, and other solid materials that range in size from nanometers to micrometers, suspended in the interstellar medium and distributed throughout the galactic disk in complex, filamentary structures. This interstellar dust, though forming only a small fraction of the galaxy's total ordinary matter, has an enormous effect on observations. It absorbs and scatters visible and ultraviolet light extremely efficiently, dimming and reddening the light of stars behind it, a phenomenon called interstellar reddening, and making large portions of the galactic disk essentially opaque to visible light observations. Interstellar dust is also the site of an important class of chemical reactions. On the cold surfaces of dust grains, simple atoms and molecules collide and stick together, gradually building up complex molecules including water, methanol, ammonia, carbon dioxide, and even simple organic compounds, providing a surface chemistry laboratory throughout the entire interstellar medium. When star-forming regions collapse and new solar systems form, the surrounding dust is incorporated into the disk of material around the young star, eventually coalescing into the rocky and icy bodies, asteroids, comets, and eventually planetary cores that make up the solid material of planetary systems, which means that interstellar dust is ultimately the raw material from which rocky planets like Earth are built. When viewed through an infrared telescope, which detects heat radiation rather than visible light, the Milky Way takes on a dramatically different appearance, with the obscuring dust of the galactic plane becoming largely transparent and the warm glow of cooler stars, dust clouds, and the central bulge becoming visible in extraordinary detail. NASA's WISE, Wide Field Infrared Survey Explorer, telescope, the Spitzer Space Telescope, and the ESA's Herschel Space Observatory have each produced comprehensive infrared maps of the Milky Way that reveal the full extent of the galactic disk, the detailed structure of the central bulge, and the positions of star-forming regions hidden behind dust clouds that are completely invisible in optical photographs. The infrared view of the Milky Way is dominated by the warm glow of the central bulge, a brilliant, oval concentration of light at the galactic center, and by the smooth, gradually fading glow of the disk, punctuated by the warm red and orange signatures of dense dust clouds and the bright, compact spots of active star-forming regions. Looking at an infrared image of our galaxy, whether the familiar WISE All-Sky Mosaic or any other comprehensive infrared survey, one gets a sense of the Milky Way's full structure in a way that no visible light image can provide, seeing the galaxy as it truly is rather than through the selective filter of what the dust happens to allow our eyes to detect. Beyond the stellar halo of old stars and globular clusters, the Milky Way is also surrounded by an enormous, diffuse reservoir of extremely hot, ionized gas known as the circumgalactic medium, a vast, near-invisible atmosphere that extends for hundreds of thousands of light-years in every direction around the visible galaxy. This circumgalactic medium was long theorized but only confirmed through X-ray observations and ultraviolet spectroscopy in recent decades, and it has been found to contain more gas than the entire visible disk of the galaxy, with temperatures ranging from tens of thousands to millions of degrees Kelvin, far too hot to form stars but warm enough to emit X-rays that can be detected with space-based observatories. The circumgalactic medium is thought to play a crucial role in the galaxy's long-term evolution, acting as a reservoir that the disk can draw upon for fresh gas to fuel ongoing star formation, and as a repository for the material driven out of the galaxy by supernova explosions and other energetic events in a continuous cycle of inflow and outflow. This vast, hot, invisible atmosphere surrounding the Milky Way is one of the most important but least visually dramatic features of our galaxy, an enormous, softly glowing cloud of plasma extending far beyond any of the galaxy's visible structures, quietly mediating the flow of matter between the galactic disk and the surrounding intergalactic space. From the vantage point of Earth's northern hemisphere, the most spectacular view of the Milky Way's central region is visible in summer evenings, when the band of the galaxy arches high overhead and the direction toward the galactic center in Sagittarius rises above the southern horizon, presenting a particularly rich and densely starred portion of the galactic sky. From the southern hemisphere, however, the galactic center rises much higher above the horizon and can be seen with extraordinary clarity on dark, clear nights. The dense, luminous heart of the galaxy blazing overhead in a way that observers in northern latitudes rarely experience, with the Milky Way arching from horizon to horizon in a continuous, breathtaking band of light. Some of the world's major astronomical observatories are located in the southern hemisphere precisely because of this clearer, higher view of the galactic center, including the European Southern Observatory's facilities in the Atacama Desert of Chile, where the extraordinarily dry, clear, high-altitude air provides conditions nearly as good as space for ground-based optical and infrared astronomy. The experience of seeing the Milky Way from a dark sky site in the southern hemisphere, the central bulge of the galaxy blazing overhead, the Magellanic Clouds floating nearby, the Southern Cross pointing toward the galactic South Pole, is considered by many astronomers and travelers to be one of the most profoundly beautiful natural sights available to human eyes. While the Milky Way Galaxy as a whole is approximately 13.6 billion years old, the thin disk, the flat, rotating structure containing most of the galaxy's stars, gas, and dust, including our own Sun, is somewhat younger, estimated to have formed approximately 8 to 9 billion years ago, after an earlier thick disk component had already assembled. The thick disk is an intermediate structure between the thin disk and the stellar halo. It contains older, somewhat more metal-poor stars than the thin disk, distributed in a somewhat more vertically extended configuration, and it is thought to represent an earlier phase of the galaxy's disk formation before the gas settled into the more compact, dynamically cooler thin disk configuration that dominates the present-day galaxy. The ages of the oldest stars in the thin disk, determined through precise measurements of their chemical compositions and the decay rates of radioactive elements within them, confirm that the thin disk has been steadily forming stars for roughly the past 8 to 9 billion years, with our own Sun forming from disk material approximately 4.6 billion years ago, roughly at the midpoint of the thin disk's existence. This means that when our Sun formed, the thin disk of the Milky Way had already been in existence for nearly 4 billion years and had already gone through multiple generations of stellar birth, enrichment, and death, providing the raw material, including all the heavy elements in our solar system, that would be needed to build a rocky planet like Earth. One of the most important discoveries in the history of galactic astronomy was made in the 1970s when astronomer Vera Rubin and her colleagues carefully measured the rotation speeds of stars and gas at various distances from the center of the Milky Way and other spiral galaxies, expecting to find that stars in the outer regions of the galaxy rotate more slowly than those closer to the center, as would be predicted by Newtonian gravity if most of the galaxy's mass were concentrated in its visible stars. Instead, they found that the rotation speeds of stars in the outer regions of galaxies remained nearly constant with increasing distance from the center, a flat rotation curve that could only be explained if there were a very large amount of additional, invisible mass distributed throughout and beyond the visible disk, providing extra gravitational pull to maintain the high orbital speeds of the outer stars. This observation became one of the most compelling pieces of evidence for the existence of dark matter. The flat rotation curves of spiral galaxies could not be explained by the visible matter alone, and the pattern fit naturally with the hypothesis of a large, roughly spherical dark matter halo surrounding each galaxy and extending far beyond its visible edge. Vera Rubin's work, though not immediately recognized with the Nobel Prize during her lifetime, is now widely regarded as one of the most consequential astronomical discoveries of the 20th century. A careful, systematic observation of how galaxies spin that fundamentally changed our understanding of what the universe is made of. When the Milky Way is viewed with X-ray telescopes, sensitive instruments capable of detecting high-energy electromagnetic radiation that is completely invisible to human eyes and is absorbed by Earth's atmosphere before reaching the ground, the galaxy reveals an entirely different face, blazing with point-like X-ray sources and diffuse, hot gas emission that tells the story of the galaxy's most energetic processes. The X-ray sky of the Milky Way is populated by binary star systems in which one star has evolved into a compact remnant, either a neutron star or a stellar mass black hole, and is actively pulling material away from its companion star in a process called accretion, which heats the infalling gas to millions of degrees and causes it to emit intense X radiation. The Chandra X-ray Observatory, launched in 1999, has produced some of the most detailed and scientifically valuable X-ray images of the Milky Way ever created, including extraordinary images of the galactic center region showing the glowing clouds of hot plasma, compact X-ray sources, and the X-ray signature of Sagittarius A** itself in remarkable detail. The X-ray view of the Milky Way is a reminder that the galaxy is not the quiet, gently glowing structure it appears to be in long-exposure optical photographs. It is simultaneously a place of soft beauty and extraordinary energetic activity, with processes occurring at temperatures and energies that dwarf anything possible in terrestrial environments. The cold, dense molecular clouds that serve as the birthplaces of stars within the Milky Way are also remarkable chemical environments, dark, frigid reservoirs of gas and dust where, despite temperatures close to absolute zero, a rich and complex chemistry is slowly unfolding on the surfaces of dust grains and in the gas phase between them. Radio astronomers have detected more than 200 distinct molecules in the interstellar medium of the Milky Way, including water, carbon monoxide, ammonia, formaldehyde, methanol, ethanol, and even complex carbon-bearing molecules like glycolaldehyde, a simple sugar, and amino acid precursors, all drifting quietly through the cold darkness of molecular clouds. The existence of these complex molecules in interstellar space is significant because it suggests that the raw chemical precursors of life, the building blocks of proteins, sugars, and nucleic acids, are not confined to the surfaces of habitable planets but are scattered throughout the galaxy, available to be incorporated into new solar systems as molecular clouds collapse and form stars. The discovery of each new interstellar molecule is something of a quiet revelation, a reminder that the chemistry of the universe does not begin on the surfaces of planets but is already underway, slowly and patiently, in the vast, cold, dark spaces between the stars that fill the Milky Way. Scattered throughout the Milky Way, in numbers that may rival or even exceed the population of true stars, are objects known as brown dwarfs, bodies that formed by the same general process as stars, from the gravitational collapse of molecular cloud material, but that did not accumulate enough mass to sustain hydrogen fusion in their cores and therefore never became proper stars. Brown dwarfs, with masses typically ranging from about 13 to 80 times the mass of Jupiter, are warm enough to fuse deuterium, a heavy form of hydrogen, for a limited period in their early lives, but they gradually cool over time as they radiate away their residual heat, eventually becoming cooler and dimmer than even the faintest red dwarf stars and approaching effective temperatures similar to a warm planet. Because of their very low luminosity, brown dwarfs are extraordinarily difficult to detect and study. They emit most of their radiation in the infrared rather than visible wavelengths, and it was only with the development of sensitive infrared telescopes in the 1990s and 2000s that astronomers were able to identify and characterize the brown dwarf population of the Milky Way in any systematic way. Current estimates suggest that brown dwarfs may constitute a significant fraction of all star-like objects in the Milky Way, perhaps as many as one brown dwarf for every 2 true stars, making them one of the most numerous categories of objects in the galaxy, quietly cooling in the darkness between the brighter stars without ever having fully ignited. High-velocity clouds are large concentrations of gas, primarily neutral hydrogen, that are observed moving through the Milky Way's halo at velocities very different from the rotational velocities of the galactic disk, suggesting that they are not simply co-rotating gas clouds within the disk but are instead material falling into the galaxy from outside or being expelled from the disk by energetic processes within it. Some high-velocity clouds are thought to be infalling material from the intergalactic medium, fresh hydrogen gas that has never been incorporated into the galaxy, slowly being drawn in by the Milky Way's gravity to potentially fuel future generations of star formation in the galactic disk. One particularly notable high-velocity cloud is the Smith cloud, a large, elongated cloud of neutral hydrogen that is currently falling toward the Milky Way's disk and is expected to impact the galactic plane in approximately 27 million years, potentially triggering a burst of new star formation in the region where it strikes. High-velocity clouds have been known since the 1960s and are still actively studied as traces of the circulation of gas between the Milky Way's disk and its surrounding halo, a slow, continuous process by which matter is exchanged between the visible galaxy and its extended, diffuse atmosphere, replenishing the disk's reservoir of star-forming material over cosmic timescales. Neutron stars, the extraordinarily dense remnants left behind after massive stars exhaust their fuel and collapse in supernova events, are among the most extreme objects in the Milky Way, compressing a mass of 1 to 2 times that of our entire Sun into a sphere with a diameter of only about 12 to 15 miles, roughly the size of a large city on Earth. Within a neutron star, the density is so extreme that ordinary atomic structure breaks down entirely. Electrons and protons are forced together to form neutrons, and the resulting material is essentially a single, enormous atomic nucleus held together by gravity rather than the nuclear forces that bind ordinary atomic nuclei. There are estimated to be roughly 1 billion neutron stars within the Milky Way, the accumulated remnants of all the massive stars that have lived and died over the galaxy's 13.6 billion year history, though the vast majority of these are old and cold enough that they no longer emit the intense radiation that would make them easily detectable, and only a small fraction of the total population has actually been found. A teaspoon of neutron star material, if somehow removed from the star and placed in ordinary conditions, would weigh approximately 1 billion metric tons, an almost literally incomprehensible density that illustrates just how extreme the endpoints of stellar evolution can be. And yet these extraordinary objects exist quietly and in enormous numbers throughout the Milky Way, the silent legacy of stars that once burned brightly. Despite containing hundreds of billions of stars and enormous reservoirs of gas and dust, the Milky Way is actually a relatively inefficient star-forming galaxy, converting only about 1 to 3 solar masses of gas into stars per year, which represents a tiny fraction of the total gas available and suggests that various physical processes are actively preventing the bulk of the galaxy's gas from collapsing into stars. This apparent inefficiency is thought to be maintained by a combination of factors including turbulence in the interstellar medium, driven by supernova explosions, stellar winds, and galactic rotation, the pressure and heat injected into the surrounding gas by newly formed massive stars, and the magnetic fields threading through the denser regions of the interstellar medium which resist gravitational collapse. The current, relatively low rate of star formation in the Milky Way represents a significant decline from the galaxy's more active past. Observations of distant galaxies in the early universe suggest that galaxies like the Milky Way were forming stars at rates 10 to 100 times higher several billion years ago, when the universe was younger and denser and more gas-rich. This long, gradual decline in star formation activity is thought to be a general feature of spiral galaxy evolution, a slow, cosmically patient, winding down as the available gas reservoir is gradually depleted and the conditions that favor vigorous star formation become progressively less prevalent over billions of years. In the direction exactly opposite the galactic center, pointed away from Sagittarius toward the constellation Auriga and Gemini, lies what astronomers call the galactic antecenter, the direction from Earth that looks outward toward the outer edge of the Milky Way's disk rather than inward toward its dense and luminous core. Looking toward the galactic antecenter, the density of stars visible in the night sky decreases noticeably compared to the direction of the galactic center, because we are looking outward toward the sparser outer disk and beyond, toward the galaxy's thinning outer rim and the vast, empty intergalactic space beyond. The outer disk of the Milky Way, in the direction of and beyond the galactic antecenter, is a region of lower stellar density, lower gas density, and lower metallicity than the inner disk. The young stars that do form out here are somewhat more metal-poor than inner disk stars, because the chemical enrichment from multiple generations of stellar evolution has had less impact in these outer, less active regions. Studying stars and gas in the direction of the galactic antecenter has been particularly valuable for mapping the extent and structure of the Milky Way's outer disk and identifying how the disk transitions into the surrounding stellar halo, helping astronomers understand where the edge of the galaxy's actively star-forming disk ends and the quieter, more diffuse halo begins. When you look at the Milky Way, you are not seeing it as it exists at this moment. You are seeing it as it was across a range of different past moments, because the light from each part of the galaxy takes a different amount of time to reach your eyes, with more distant parts appearing as they were further in the past. The stars nearest to our solar system appear as they were just a few years ago, while the stars in the central bulge of the galaxy appear as they were approximately 26,000 years ago, and the stars along the outermost spiral arms visible to the eye appear as they were perhaps 50,000 to 70,000 years ago, meaning the view of the Milky Way you see is a composite of dozens of different historical epochs, all presented simultaneously as a single, unified view. This is true of every observation of the universe at every scale. Astronomy is inherently a form of time travel, with greater distances corresponding to greater looks into the past. But it is particularly striking when applied to the Milky Way, since the distances involved are large enough that the time delays correspond to meaningful human-scale history. The light from the galactic center that is reaching your eyes right now began its journey approximately 26,000 years ago, at a time when human civilization had not yet invented agriculture, when the ice sheets of the last glacial maximum were still retreating, and when the population of the entire Earth was measured in millions rather than billions. Looking ahead billions of years into the future, astronomers can make informed projections about the Milky Way's star formation trajectory based on current measurements of the galaxy's gas content, the rate at which that gas is being consumed, and the rate at which it is being replenished by inflows from the surrounding halo. The current consensus among astronomers is that the Milky Way's star formation rate will continue to gradually decline over the next several billion years as its supply of cold molecular gas is slowly depleted. A gentle, prolonged sunset of stellar birth that will not end abruptly but will fade slowly and continuously over an enormous span of cosmic time. This does not mean the galaxy will become completely dark in the foreseeable future. The long-lived red dwarf stars being born today will burn steadily for tens to hundreds of billions of years, ensuring that the Milky Way will remain populated with cool, slowly glowing stars long after the more massive, brighter stars have all exhausted their fuel and ended their lives. In the very distant future, trillions of years from now, after the eventual merger with Andromeda, has reshaped the galaxy into an elliptical structure, and the last available gas has been converted into stars. The Milky Way as we know it will have become a vast, slowly dimming collection of aging stars, their light growing ever redder and fainter as the long, quiet twilight of our galaxy deepens. Long before modern astronomy existed, the cultures of the ancient world observed the Milky Way carefully and with great sophistication, weaving its appearance and behavior into their cosmologies, navigation systems, agricultural calendars, and sacred stories in ways that demonstrated deep and continuous engagement with the night sky stretching back across thousands of years. In ancient Egypt, the Milky Way was associated with the goddess Nut, the sky goddess who arched her body over the earth, and the Milky Way was sometimes depicted as a heavenly river, a celestial counterpart to the life-giving Nile that flowed below. The ancient Greeks developed sophisticated theoretical accounts of the Milky Way's nature. Democritus proposed in the 5th century BCE that the Milky Way was composed of a vast multitude of stars that were individually too faint to resolve with the naked eye, a remarkably accurate intuition that would not be confirmed until Galileo turned his telescope to the sky in 1610 and resolved the Milky Way into individual stars for the first time. The Lakota people of North America described the Milky Way as the Wanagi Takanku or Spirit Road, the path along which the souls of the deceased traveled after death, while Aboriginal Australians developed one of the world's most sophisticated dark sky astronomy traditions, identifying the dark nebulae along the Milky Way as animal constellations whose rising and setting marked seasonal changes and guided food-gathering activities. In 1610, Galileo Galilei, using one of the earliest telescopes ever turned toward the night sky, pointed his instrument toward the soft, luminous band of the Milky Way and made an observation that would permanently alter humanity's understanding of the cosmos. The apparently continuous, milky glow resolved, under telescopic magnification, into an uncountable multitude of individual faint stars, packed so closely together that the naked eye could not separate them. This observation confirmed the ancient hypothesis of Democritus that the Milky Way was composed of stars rather than gas, cloud, or some other continuous substance, and opened the door to the understanding that the galaxy is not a special, unique cosmological feature but a vast collection of the same kinds of objects that appear as individual stars throughout the rest of the sky. Galileo recorded his observation in his landmark work Sidereus Nuncius, the Starry Messenger, writing that the galaxy was in fact nothing but a congeries of innumerable stars grouped together in clusters, a modest, precise phrase that contained within it a profound transformation in humanity's picture of its cosmic home. The moment Galileo described in those quiet words marked the beginning of the end of the pre-telescopic era of astronomy and the start of a process of discovery that would eventually lead, through 3 more centuries of accumulated observation and insight, to our current understanding of the Milky Way as a vast barred spiral galaxy among hundreds of billions of similar galaxies in the observable universe. When the entire sky is surveyed at gamma-ray energies, the most energetic form of electromagnetic radiation, the Milky Way appears as a bright, glowing band of diffuse emission running across the sky, produced by the interaction of cosmic ray particles with the gas and interstellar radiation field throughout the galactic disk. This diffuse gamma-ray emission is one of the most important observational probes of the cosmic ray environment throughout the galaxy. By mapping how the intensity and energy distribution of the gamma-ray emission varies across the galactic disk, astronomers can reconstruct the 3-dimensional distribution of cosmic rays and the properties of the interstellar medium through which they propagate. Superimposed on this diffuse galactic background are hundreds of discrete, point-like gamma-ray sources, pulsars, remnants of supernova explosions, accreting compact objects, and very high-energy particle accelerators of various types. Each one a separate bright point on the gamma-ray sky that represents some energetic physical process occurring within the galaxy. The gamma-ray sky of the Milky Way is primarily known through the observations of the Fermi Gamma-Ray Space Telescope, launched in 2008, which has produced the most detailed and comprehensive all-sky gamma-ray maps ever constructed, revealing a galaxy that is continuously, pervasively active at energies far beyond what any visible light observation would suggest. Just as archaeologists can learn about ancient human civilizations by studying the artifacts and structures they left behind, astronomers use what is sometimes called galactic archaeology, the careful study of the chemical compositions, ages, and motions of stars throughout the Milky Way, to reconstruct the history of the galaxy's formation and assembly over billions of years. Stars retain in their chemical compositions a detailed record of the conditions in the gas from which they formed, including the metallicity of the interstellar medium at the time and place of their birth, and by studying large samples of stars with precisely measured chemical compositions, astronomers can identify populations of stars that formed together in the same environment even if they have since dispersed across the galaxy. This technique of chemical tagging, identifying groups of stars with matching chemical fingerprints that mark them as siblings born from the same molecular cloud, is one of the most powerful approaches to understanding the Milky Way's star formation history, since it allows astronomers to effectively reverse the clock on the dispersal of star clusters and recover the record of past star formation that is otherwise hidden by billions of years of orbital mixing. Surveys like the Gala survey in Australia and Apogee in the United States have measured the detailed chemical compositions of hundreds of thousands of individual stars across the Milky Way, assembling a chemical census of the galaxy that is gradually revealing its birth history star by star, one careful measurement at a time. In the ancient astronomical traditions of India, some of the oldest and most mathematically sophisticated in the world, the Milky Way was known as Akasha in Sanskrit, meaning the Ganges of the sky or the heavenly Ganges, a name that draws a beautiful parallel between the galaxy's soft, flowing appearance in the night sky and the sacred river that has been at the center of Indian cultural and spiritual life for thousands of years. The Vedic and later Hindu astronomical texts known as the Vedangas and the Siddhanta tradition developed remarkably precise methods for measuring and predicting the positions of stars, planets, and the movements of the sun and moon across the background of stars, using mathematical techniques that were among the most advanced in the ancient world. The great Indian mathematician and astronomer Aryabhata, writing in the 5th century CE, proposed that the Earth rotates on its own axis, a concept not widely accepted in European astronomy until Copernicus, and his work on the motions of celestial bodies was deeply integrated with careful observations of the galaxy's band as a reference framework for tracking the positions of stars and planets throughout the year. The name Akasha endures in South Asian languages and cultures to this day, a poetic, beautiful designation for our galaxy that reflects both the deep reverence with which its ancient astronomers regarded the sky and the timeless, flowing quality of the Milky Way's appearance on a clear, dark night. The history of radio astronomy, the science of observing the universe through radio waves rather than visible light, is intimately connected with the Milky Way, as it was the accidental detection of radio emission from the galactic center that first revealed that the universe was not silent at radio wavelengths and opened an entirely new window on cosmic phenomena. In 1932, Karl Jansky, an engineer at Bell Telephone Laboratories who had been tasked with identifying sources of radio interference affecting transatlantic telephone communications, detected a persistent, regular source of radio static that he eventually traced to the direction of the center of the Milky Way in Sagittarius, correctly identifying it as extraterrestrial in origin. Jansky's discovery was followed up by amateur astronomer Grote Reber, who built the world's first purpose-built radio telescope in his backyard in Illinois in 1937 and produced the first detailed radio maps of the Milky Way, showing that the galactic plane and center were the strongest sources of radio emission in the sky. These early radio astronomy observations of the Milky Way were the seed from which an entirely new branch of astronomy grew, one that would eventually reveal pulsars, quasars, the cosmic microwave background radiation, and the large-scale structure of the universe, all of it growing from that first quiet, accidental detection of the galaxy's radio voice. The region of the Milky Way immediately surrounding our solar system, a volume extending perhaps 1,000 light-years in every direction, has been studied in extraordinary detail through nearby stellar surveys, and the chemical composition of nearby stars has been found to vary in ways that reflect both local star formation history and the broader galactic metallicity gradient. Stars in the immediate solar neighborhood span a wide range of ages, from young, hot, blue stars formed within the past few million years in nearby star-forming regions, to old, cool, red dwarf stars that have been burning quietly since before the solar system was born. And this age spread is reflected in a corresponding spread of metallicities, with older stars generally having lower metal content than younger ones. The metallicity of the interstellar medium in our galactic neighborhood is sufficient to supply new star-forming regions with a generous abundance of heavy elements, meaning that any rocky planets forming from molecular clouds in this region of the galaxy today would have access to essentially the same palette of elements that formed Earth and provided the chemical foundation for life as we know it. This local chemical richness is both the product of billions of years of stellar processing, cycles of stellar birth, nuclear burning, and element dispersal that began long before our solar system formed, and the resource base for whatever new planetary systems and potential future life forms might emerge from the star-forming regions that still exist in our quiet corner of the Milky Way. While Sagittarius A*, the supermassive black hole at the center of the Milky Way, is currently in a relatively quiet, low luminosity state, consuming only small amounts of surrounding material, it has almost certainly been far more active in the past and may again become more active in the future as new sources of material become available to fall within its gravitational reach. The Fermi bubbles described earlier are considered strong evidence that Sagittarius A* underwent a period of significantly elevated activity, perhaps a million-fold increase in luminosity compared to today, within the past few million to tens of millions of years, driven by either a period of intense gas accretion or a burst of concentrated star formation near the galactic center. Looking ahead, the predicted merger of the Milky Way with the Andromeda Galaxy in approximately 4 to 5 billion years is expected to dramatically increase the amount of gas available near the merged galaxy's center, potentially triggering a period of intense black hole activity as the merging galaxy funnels large quantities of fresh material toward the central region. Despite its quiet current phase, Sagittarius A* will always exert its gravitational dominion over the center of the Milky Way, a permanent, patient presence at the heart of the galaxy, the unseen anchor around which hundreds of billions of stars have been slowly orbiting for billions of years, and around which they will continue to orbit for billions more. The Milky Way is not only a member of the local group but is also part of a much larger cosmic structure known as the Virgo supercluster, a collection of more than 100 galaxy groups and clusters spread across a region of space approximately 110 million light-years in diameter, centered on the massive Virgo cluster, one of the nearest large galaxy clusters to our local group. The Virgo supercluster, in turn, has been revealed by more recent observations to be only one lobe of an even vaster cosmic structure known as the Laniakea supercluster, a supercluster of superclusters spanning approximately 520 million light-years in its greatest extent and containing an estimated 100,000 individual galaxies including the Milky Way, the Andromeda Galaxy, and all the members of the local group. Within the Laniakea supercluster, galaxies are not uniformly distributed but are arranged in a web-like pattern of sheets, filaments, and clusters, the cosmic web, with large voids of relatively empty space between the denser regions, a pattern that reflects the large-scale structure of the universe as shaped by dark matter and the initial density fluctuations left over from the very early universe. The name Laniakea comes from the Hawaiian words meaning immeasurable heaven, a name chosen to reflect both the extraordinary scale of this cosmic structure and the tradition of Polynesian navigation by the stars, a fitting tribute given that the Milky Way and its neighbors have been guiding human beings across the Pacific Ocean for thousands of years. The dust lanes that sweep through the Milky Way's spiral arms, those long, sinuous dark structures that absorb the light of more distant stars and create the visual contrast that gives the galaxy its intricate, layered appearance in deep photographs, are not simply obstacles to astronomical observation but are among the most scientifically important and aesthetically compelling features of the galaxy. In visible light photographs of the Milky Way, the dust lanes appear as dark, quiet rivers flowing through a sea of stars, twisting and branching through the spiral arms, sometimes completely obscuring the rich star fields behind them, creating a depth and texture to the galaxy's appearance that a purely star-filled image would lack. These dark lanes correspond to the locations of the densest molecular cloud complexes within the spiral arms, the very regions most actively involved in forming new stars, meaning that the darkest, most light-absorbing features of the galaxy are simultaneously its most actively creative regions, the places where the next generation of suns and planetary systems are slowly assembling themselves in the cold and dark. There is a quiet beauty in this contrast. The darkest features of the galaxy are also the most generative, the most expectant with future light. A reminder that darkness and the potential for illumination often occupy the same space, in the Milky Way as perhaps in other contexts as well. Long before modern radio and infrared astronomy revealed the true extent and structure of the Milky Way, early astronomers using naked eye observations and the first generations of telescopes made remarkably thoughtful attempts to understand the distribution of stars in space and to infer from it the shape and extent of the stellar system we inhabit. William Herschel, in the late 18th century, undertook the first systematic attempt to map the shape of the Milky Way by counting the number of stars visible in different directions of the sky, a technique called star gauging, and concluded that the stellar system was disk-shaped and that the Sun was located somewhere near its center, a conclusion that was partially correct in geometry, but significantly incorrect about the Sun's central position. Herschel's star gauges gave a picture of the galaxy as a flattened, somewhat irregular disk with the Sun near the center, an understandable error, given that the dust clouds obscuring the view of the galactic center prevented Herschel from seeing the far richer and more densely populated inner regions of the galaxy, making the Sun's position appear more central than it actually is. Herschel's work was nonetheless a milestone, the first serious, systematic attempt to understand the three-dimensional structure of the Milky Way through observational data, and it established the framework of questions and methods that subsequent generations of astronomers would refine, correct, and enormously expand over the following century and a half. While our galaxy is moving toward the Great Attractor, there is an even more fundamental measurement of the Milky Way's motion, its velocity relative to the cosmic microwave background, CMB, the afterglow of light from the Big Bang that permeates the entire universe and serves as the most fundamental reference frame available to cosmology. The CMB appears very slightly hotter in the direction the Milky Way is moving toward and slightly cooler in the direction away, a dipole anisotropy in the CMB temperature, and measurements of this dipole indicate that our local group of galaxies, including the Milky Way, is moving relative to the CMB frame at a speed of approximately 1.3 million miles per hour in the direction of the constellations Leo and Virgo. This motion is the sum of multiple components: the Earth's orbit around the Sun, the Sun's orbit around the galactic center, and the Milky Way's motion as part of the local group and its larger-scale flow toward the Great Attractor and within the Laniakea supercluster, all adding up to our total velocity relative to the most fundamental background of the universe. The CMB dipole measurement provides the most precise available determination of the absolute motion of the Milky Way through the cosmos, a reminder that even in the largest context, the galaxy is not standing still but is moving purposefully through the universe, carried along by the great currents of large-scale cosmic structure. In addition to the supermassive black hole Sagittarius A** at the galactic center, the Milky Way also contains an enormous population of stellar mass black holes, the compact remnants left behind when the most massive stars in the galaxy exhaust their fuel and collapse, producing objects with masses ranging from about 3 to several dozen times the mass of the Sun, compressed into regions smaller than a city. Based on the number of massive stars that have lived and died in the Milky Way over its 13.6 billion-year history, astronomers estimate that there may be somewhere between 10 million and 1 billion stellar mass black holes scattered throughout the galactic disk and halo, most of them completely isolated and invisible in the darkness between the stars, quietly warping the space-time around them without any infalling material to betray their presence. The existence of large populations of stellar mass black holes in the Milky Way was dramatically confirmed in 2015 when the LIGO gravitational wave detector recorded for the first time the gravitational waves produced by the merger of two such black holes approximately 1.3 billion light-years from Earth, opening an entirely new window on the black hole population of the universe through gravitational wave astronomy. Black holes found in binary systems with companion stars, where infalling material heats up and emits X-rays before crossing the event horizon, have been detected and studied in the Milky Way for decades, providing detailed measurements of black hole masses and properties that have confirmed many predictions of general relativity theory. Compared to many other galaxies of similar size and mass, the Milky Way appears to be in an unusually quiet, settled state, with a relatively low current star formation rate, a dormant rather than active central black hole, and a relatively undisturbed disk structure that suggests the galaxy has not experienced a major merger event or other catastrophic disturbance for several billion years. This long period of relative tranquility is thought to be one of the factors that has allowed complex life to develop and persist on Earth, a planet that has needed roughly 4 billion years of continuous, stable conditions to evolve from the first single-celled organisms to the complex, technologically capable life forms that exist today. If the Milky Way had experienced a major galactic merger, a period of intense quasar activity from Sagittarius A*, or a dramatically elevated supernova rate in the recent geological past, the resulting radiation, gravitational disturbances, and environmental changes could potentially have disrupted the stable conditions that allowed life on Earth to persist and evolve uninterrupted. There is something quietly comforting about this picture, our galaxy's relative peacefulness, its long, undisturbed rotation and gentle, steady star formation, as a contributing factor in the long, patient story of life on our small planet, the galaxy providing the stable background against which billions of years of biological evolution could quietly unfold. The oldest individual stars so far identified within the Milky Way are ancient, metal-poor stars that formed in the galaxy's earliest epochs, some of them carrying chemical compositions so primitive, with such low abundances of elements heavier than hydrogen and helium, that they preserve a nearly pristine record of the chemistry of the very early universe. One of the oldest known stars in the Milky Way is a red giant called Methuselah star, or HD 140283, located approximately 190 light-years from Earth in the constellation Libra. A star whose age has been estimated through precise measurements of its chemical composition and luminosity at approximately 14.5 billion years, with an uncertainty that allows it to be consistent with the age of the universe itself. Another extraordinarily ancient star, SMSSJ 031300.36-6708339.3, located in the Milky Way's halo and discovered by the SkyMapper survey in 2014, has a measured iron abundance so extraordinarily low, about 10 million times lower than that of our Sun, that it may be a second-generation star that formed from material enriched by only a single first-generation supernova event in the earliest moments of the galaxy's history. These ancient stellar relics, surviving fossils of the galaxy's earliest formation epochs, provide astronomers with a direct observational window into conditions in the Milky Way and the universe that would otherwise be completely inaccessible, their chemical compositions frozen in time as a record of the galaxy's primordial state. The very outer edge of the Milky Way's disk, beyond the well-defined spiral arm structure of the inner and middle galaxy, gradually thins and becomes increasingly irregular, with a sparser population of older stars, small pockets of star formation, and increasingly diffuse gas that fades slowly into the surrounding intergalactic medium. The exact boundary of the Milky Way's disk is somewhat difficult to define precisely, in part because the transition from the galaxy to the surrounding medium is gradual rather than sharp. The disk does not simply stop at a defined edge but instead thins exponentially with increasing distance from the center, growing progressively sparser until individual stars and gas clouds are separated by ever larger stretches of essentially empty space. Studies of the outer disk have revealed that it extends significantly farther than originally thought. Some surveys have found coherent stellar structures out to distances of 60,000 to 75,000 light-years from the galactic center, suggesting that the outer disk, while very sparse, reaches much closer to the expected edge of the galaxy's 100,000 light-year diameter than earlier estimates placed it. The outer disk of the Milky Way is one of the most frontier regions of galactic astronomy, a poorly mapped, sparsely populated, quiet region of the galaxy where the density of stars gradually gives way to the near-emptiness of intergalactic space, like the shore of a vast, star-filled ocean gradually merging with an infinitely larger, quieter sea. Every heavier element in the observable universe, every atom of carbon, oxygen, silicon, iron, gold, silver, and uranium, was produced inside the cores of stars or in the explosive death events of stars, and the Milky Way, over its 13.6 billion-year lifetime, has been one of the most productive factories for these elements in the local universe. The total mass of heavy elements produced by the Milky Way over its history is estimated at several billion solar masses, distributed throughout the galaxy's interstellar medium by stellar winds and supernova explosions, gradually enriching each successive generation of star-forming molecular clouds and the planetary systems that form within them. The gold in jewelry, the uranium in nuclear reactors, the iron in the hemoglobin that carries oxygen through your bloodstream, all of it has a history that traces back through the interstellar medium of the Milky Way and ultimately to the interiors of stars that lived and died long before our solar system was born. The Milky Way is, in this very literal sense, not merely the home of life on Earth but one of the conditions that made life possible. The chemical factory whose billions of years of stellar processing produced the diversity of elements that life requires, and whose patient operation over cosmic timescales built up the raw materials for everything that exists on the surface of our world today. If you could position yourself directly above or below the Milky Way's disk, traveling perpendicular to the plane of the galaxy to look straight down at its face, you would see the full, breathtaking structure of the barred spiral in its entirety. The central bar and its surrounding bright core, the four major spiral arms sweeping outward in graceful, symmetrical curves, and the fainter, more diffuse outer disk gradually fading at the edges. This is a view that no human has ever had and that will remain beyond human reach for the foreseeable future. Given the distances involved, the galactic North Pole lies approximately 300 light-years above the galactic plane as measured from the Sun's position. But the full face-on view would require a distance of at least 100,000 light-years from the galactic plane to encompass the entire disk. The nearest analog we can observe is other similar face-on spiral galaxies. Galaxies like the Pinwheel Galaxy, M101, the Whirlpool Galaxy, M51, or the Triangulum Galaxy, M33. Which are oriented close enough to face on relative to our line of sight to give a general impression of what the Milky Way might look like from a great vertical distance. Looking at these nearby face-on spirals through a telescope on a dark, clear night, their soft, luminous arms sweeping outward from a glowing central core, is perhaps the closest available approximation to seeing the Milky Way from the outside. And it is an experience that tends to inspire a particular, quiet wonder at the beauty of the structure we are embedded within. Within the molecular clouds of the Milky Way where stars are born, the magnetic fields threading through the dense gas play a subtle but important role in shaping the process of stellar formation, resisting the gravitational collapse of overdense regions by providing a magnetic pressure that partially counteracts the inward pull of gravity and must be overcome before star formation can proceed. The competition between gravity and magnetic pressure in star-forming molecular clouds results in a process of ambipolar diffusion, a slow, gradual drift of neutral gas relative to the ions that are coupled to the magnetic field lines, which effectively allows the gas to slowly leak across field lines and accumulate in dense clumps, on timescales of millions of years, until gravity finally wins and collapse begins. This magnetically regulated star formation process is one of the reasons why star formation is as slow and inefficient as it is. Without the braking effect of magnetic fields, the dense gas in molecular clouds might collapse much more quickly and convert into stars at a far higher rate than is actually observed throughout the Milky Way. Observations of the polarization of infrared and radio emission from molecular clouds, which reveals the orientation of magnetic field lines within the clouds, have allowed astronomers to map the magnetic field structure within star-forming regions and test theoretical models of magnetically regulated star formation with increasing precision over the past several decades. Among the richest and most active star-forming regions in the Milky Way visible from the northern hemisphere is the Cygnus X complex, a large, complex region of active star formation located within the Cygnus spiral arm at a distance of approximately 4,600 light-years from Earth, making it one of the nearest major regions of high-mass star formation to our solar system. The Cygnus X region contains several large associations of young, massive stars, hot, luminous blue and white giants that formed within the past few million years, along with extensive ionized gas clouds, molecular cloud remnants, and the energetic remnants of stars that have already lived and died during the region's recent star formation history. The intense ultraviolet radiation from the massive young stars in Cygnus X has carved large, glowing cavities in the surrounding molecular cloud material, creating a dramatic landscape of glowing filaments, pillars of denser material resisting erosion, and bright ionization fronts where the radiation meets fresh molecular cloud gas, a dynamic, constantly evolving tableau of stellar feedback reshaping the very environment in which it was born. The Cygnus X region is sufficiently close and active that it has become one of the most studied star-forming regions in the Milky Way, serving as a laboratory for understanding how the formation of massive stars affects their surrounding molecular cloud environment and for testing theories of stellar feedback and the regulation of star formation. And so, we have journeyed together through 100 quiet windows into the life of our galaxy. A galaxy that is ancient and enormous and deeply, endlessly beautiful. Tonight, whether the stars are visible above you or hidden behind clouds, they are still there, hundreds of billions of them, patiently shining in the great slow turning of the Milky Way, as they have been for billions of years before this moment and will be for billions of years to come. You belong to this galaxy, made of its oldest light and its most patient atoms, and tonight, it holds you gently in its quiet, invisible arms as you rest. Sleep well, stargazer. The Milky Way will be right there when you wake.